I'm Tim Ferguson,
I'm Evan Knapp.
I'm Adam Costi.
and our project is about the tolerances on capacitors, more the true tolerance, because all manufacturers produce capacitors of many different types, and a lot of times they have different types of capacitance ranges. So we're going to kind of test and see how accurate they are. So, like I said before, all capacitors are given a tolerance range specified by the manufacturer, and these can range from anywhere from 1% up to 20%. And that's very specific on what kind of capacitor you have and what the voltage rating is. So our three types of capacitors that we're using is electrolytic, ceramic, and polypropylene. And for voltage ratings, our electrolytic capacitors were rated for 50 volts, and so were the ceramic capacitors, and the polypropylene were also rated for 50 volts. And this is important because this is very unique for each capacitor, and different types of capacitors all have different physical characteristics that really determine kind of how they're going to respond and in terms of accuracy. It's impossible to create a perfect capacitor because obviously materials aren't perfect, they have impurities, and the manufacturing processes aren't always perfect either. Sometimes you need precision down to the nanometer, and it's really hard to obviously be accurate when you're at those kinds of tolerances. So our goal for this project is to make a confidence interval on the tolerance of the capacitors, because the manufacturer has a stated tolerance range for each type of capacitor, but we want to kind of investigate it ourselves and see how accurate these are. So we have three types of capacitors, as I said before: electrolytic, ceramic, and polypropylene. And we want to see, of these three types of capacitors, which capacitor is more likely to be where you would expect it to be.
Alright, so as Tim said before, we looked at three different types of capacitors. A little about electrolytic capacitors. They tend to be about 20% in tolerance because they're usually used to have higher capacitances, about from 0.1 microfarad to 2.7 farads, which is absolutely huge as far as capacitances are concerned. Electrolytic capacitors are usually used in power circuits, and they're hold large amounts of energy because they have the high capacitances. And they're typically constructed from aluminum, tantalum, and niobium. So the second type of capacitor we'll look at are monolithic multi-layer ceramic capacitors. These capacitors are the most widely produced in the world. There's two different classes of these capacitors. There's the class 1, which are highly stable and have low losses in resonance circuits. And the second one, and the class 2 capacitors, have higher efficiency for smoothing, bypass applications, coupling and decoupling applications. And they typically have a tolerance range from 5 to 10% and tend to range in value from 10 picofarad to 100 microfarad. The third type of capacitor we looked at are polypropylene capacitors, otherwise known as film capacitors. And their tolerance ratings tend to change depending on the differences, and it's called an E series. And the normal range will stem from either 1% to 20% in variance and tolerance, and that's again dependent on the type of E series it is. And they're most commonly used in like microelectric circuits that are AC or DC and are constructed from plastic films.
Alright, so now we're going to talk a little bit about how we collected the data and the ways that we used the data and interpreted the data using the program that we've been using all semester, MATLAB. So, we started off by taking 80 preliminary samples from each of the three categories that was stated before: the electrolytic, the ceramic, and the polypropylene. We took 4 different values, at least to start off with, from each category, and we took 20 samples from all of the 4 different values, which is what gives you what we have up here as our 80 samples per channel. So we used MATLAB to kind of organize our data, find our sample means, our standard deviations, and and everything of that nature in order to find histograms, see if any of these samples followed a normal fit distribution, which actually we found out that they didn't fit so much of a normal distribution fitting. It was more of an exponential fit, which we also used MATLAB. There was a function which everyone has kind of used in the fourth project that we did, which is called hist fit, and we did an exponential fit to a lot of our graphs to kind of see how that would work out. The distribution that we ended up having to use in order to find our confidence intervals, though, was actually something that we found online as a little bit of a different type of distribution. It's called the bootstrap distribution. The purpose of this distribution is to allow for a more natural use of the sample, the data from the samples, rather than assuming that it's going to be a normal fit distribution. So we're going to start off first by talking about our electrolytic capacitors and a little bit of our data collection. As you can maybe kind of make out in the background here, it's just kind of some of our data, just showing you a little bit of an idea of what we were collecting. But the values we tested, so far we've actually only tested the 100 nano, the 1 micro, the 10 micro, and the 6.2 nanofarad capacitors. We are going to test another sample just to kind of try and verify our data for our final report. But our tolerances were plus or minus 20%. We actually looked at it as an absolute value of the percentage, not the plus or minus. That kind of gave us a better way to evaluate the histograms and the his-fit data. This right here is our first set of histograms with adjusted bins depending on the amount of samples and the way that the samples were actually fitting the distributions. As you can see on the left here, you can't really pick out what kind of distribution we're going to be having. I mean, if you look at the top left one, that almost looks like it could be a normal fit distribution, where the one to the right of it looks almost exponential in nature. So as you can see, 20 samples per piece kind of wasn't enough, so we decided to actually analyze all the different measured values as one collective case. As you can see, as the collective case, you can start to see an exponential decay occurring. Something else, I guess, to notice would be that as we kind of got further up in our capacitor values, it tended to kind of skew away from anything that we could really have as a finite, fit to any of the distributions. As you can see, the 100 nanofarad, we actually had kind of a normal fit, whereas once you got to the 47 microfarad, there wasn't really any fit that we could define. So this here is kind of like what I was saying. We looked into exponential fit for all of our graphs because that's kind of what we predicted the fit would look like if manufacturers were actually agreeing with their tolerances and doing what they were supposed to be doing. So as you can see on the right, that is our completed set of all the electrolytic capacitors, and right down here we have our p-value. That is actually our confidence interval, which we calculated in this case. We were 92.57% confident that it would fall between 0.06% and 20% of our error, which is the electrolytics are plus or minus 20%. So as you can see, the electrolytics definitely fell. They were pretty accurate in their representation of their confidence interval.
So the second type of capacitor that we tested are the ceramic capacitors, and once again, some of the data is in the background. You probably can't see that. The values we tested are 68 picofarad, 100 nanofarad, 1 microfarad, and 10 microfarad. And the tolerance on the specific capacitors that we used is plus or minus 5%. So, kind of like before, we have each different value of capacitor individually as a histogram so that you can kind of see where the data lies. And these graphs are in terms of their percent away from the accepted range. So for example, there was a lot of capacitors in the lower end of the tolerance range, and then as you got farther out, there tended to be less. So the first graph, you can see that there's almost an exponential fit, but all four of them aren't similar in their distribution, which is why we had to analyze them as a collective like before. And as you can see, it tends to go towards an exponential fit. And then this data here, it's almost like a normal fit distribution, but we can't exactly say that the capacitors follow that distribution as a whole because obviously each different range of capacitances yielded a different type of distribution. So this is the same exact data, but now we fit a line to it using MATLAB, just so you can kind of see what we are talking about graphically. you can see that in the first category of capacitors, the 68 pico, it actually fits a exponential fit. But you can see as the capacitance changes, it's very inconsistent. And in terms of the percentage that ceramic capacitors are supposed to be in, they have a tolerance of 5%. So a lot of this data represents capacitors that are far out of that range. And looking at the data as a collective, it also fits an exponential fit, but we were unable to determine a confidence interval because so much of the data that we collected is out of the range of the tolerance for the capacitors. And this is due to just lack of samples, so more samples would correct this.
The last type of capacitor we looked at was the polypropylene. And these capacitors, we tested the values of 4.7 nanofarads, 5.6 nanofarads, 6.2 nanofarads, and 8.2 microfarads. And on these specific capacitors, they had a tolerance of 5%. If you look at the data, the 4.7 nanofarad capacitors seem to follow an exponential fit for their values we collected. And the 6.8 nanofarad also kind of has an exponential fit, as well as the 8.2 microfarad, but it does not. As you can see, it has this bin right here from 0 to 1. And then obviously the top right clearly isn't an exponential fit. But if you look at the trend in our overall data with the collective, putting them in one collective histogram, it does have that nice exponential fit. If you look at the data we have for these polypropylene capacitors, the exponential trend line does fit quite nicely with all our data. Well, not all of it, but most of it. And we had a confidence interval of 99.99% because the data we collected was all under 5% tolerance, and which means we have a 99.99% chance if we selected one of the 80 capacitors we tested at random that the tolerance range would be within 0.0179% to 4.7447%.
So this right here, yes, analytically it's not as important, but we did kind of want to look at the significance of all of the data that we collected. So this is all our measured capacitors over all the different categories. As you can see, a nice exponential fit was, accustomed to this, but it's not nearly as impactful considering the fact that all these different capacitors had different measured tolerances. We just kind of wanted to analyze that data just to kind of, take a look at everything we collected. And then here is kind of our trend line we fit to it. As you can see, it fit almost perfectly to an exponential fit. It's a very good fit. And we just want to look at the confidence interval overall, just kind of see what our range was. So we just picked a value that's kind of a standard value, which is a 95% confidence interval. Out of all the capacitors that we measured, we could be 95% confident that between 0.08 and 23.25% would be our error in the capacitors that we chose for this project, as far as any of the capacitor values went.
Some things we could improve on in the future, or for when we're writing our lab report, is we can test a wider range of capacitor values instead of just testing the 4 we did. So, as I said earlier, that some of the capacitors have different ranges of values they're typically at, and once you get to towards the extremes, max and mins, they might not be. They're
Towards the maximums, they tend to be farther off.
right. So some things we can improve on for when we have to write our report on the topic is we can test a wider range of values instead of just doing the 4 that we did for each capacitors. We can actually test more around the spectrum of the values of the capacitances that they usually are instead of testing like around the max and min values of the capacitances, because they tend to get a little, the numbers tend to get spotty once you go towards the extremes. Another thing is we can acquire more samples, test more capacitors than the 20 we did for each. Maybe we could do 40 each. And also, we need to gather more data for the ceramic capacitors because we weren't even able to come up with a confidence interval because all the data we collected was just, it didn't give us enough to have a good result.
So in conclusion, the polypropylene had the best chance of being in tolerance or where we expected them to be. And that could also be due to the fact that the data we collected for ceramic capacitors wasn't ideal. We weren't able to come up with a confidence interval for ceramic capacitors because, as Adam said, they were all too far off. But the polypropylene capacitors, I don't think we had one that fell out of range. The electrolytic capacitors were also really good, but that can also be attributed to the fact that they have they're much more forgiving in terms of tolerance. A 20% tolerance range is much easier to work with than a 5% range or a 1% range. So it makes sense that they would appear to be better. Yeah, and this is just some data. This data represents all of the standard deviations, the sample sizes, the variance, and the sample means for all the different types of capacitors that we collected. And this is just some of the MATLAB code and some of the extra data we got. Like, this is all the confidence intervals that we collected, and then their corresponding, or these are the confidence intervals, and these are how confident we are about those intervals.